Hello physicists and welcome. In this session we'll be covering section 11, additional practice, motion maps, graphing, and proportional reasoning, found on page 17 of the packet. Let's get started. Hey, in A we're looking at a bicycle is moving at a speed of 5 meters per second. How much time does it take for the bike to travel 15 meters? Hey, I know my relationship. My velocity times my time is equal to my displacement. In this case, I'm looking for time, so I'm going to divide each side by velocity. So I know my time is equal to my displacement divided by my velocity. In this case, 15 meters divided by 5 meters per second tells me my time is equal to 3 seconds. Let's go ahead and transfer that over to the time and position table. So at a time of 0, I'm going to assume I started at a position of 0. 1 second later, traveling at 5 meters per second, I'm at a position of 5 meters. At 2 seconds, I'm at a position of 10 meters. And at a time of 3 seconds, I'm at 15 meters. Now we'll go ahead and calculate our velocity for each of those positions. I know my velocity is equal to my change of position since the last measurement divided by my change of time. Hey, so I'm at a time of 0. I'll need to get to my second position here, or my second time interval, to get a change of position and a change of time. So let's take a look at this. So I've gone from 0 to 5 meters. That's a change of position of 5 meters divided by 1 second. So I'm going 5 meters per second. How about to my next second? I go from 1 to 2 seconds. That's 1 second. I went from 5 to 10 meters. That's a change of 5 meters. 5 meters divided by 1 second. You can see I'm still going 5 meters per second. And at 3 seconds, we can calculate the same. 5 meters per second. I'm going to hold off making the position versus time and velocity versus time graphs until I have enough information to find out what range I need for velocity and for position. So let's come back up here and we'll take a look at B. So we're asking, hey, at what speed would the bicycle need to travel to cover the same distance in twice the time? Let's come on down to our proportional reasoning. Hey, so we're looking for speed or velocity here. We want to cover the same distance. So same has the number 1, and we want to be in twice the time. So 2 times. So we'll look at the new proportion for our velocity. Same distance, twice the time, 1/2. So our velocity for B will be 1/2 the velocity of A. Let's go ahead and calculate that. So my new coefficient from here, 1/2. My variable is V. So my coefficient, 1/2 times the original value, 5 meters per second, gives us our new value, 2.5 meters per second. Let's go ahead and calculate that time now that we'll need. So we're saying 2 times our original time, 2 times 3 seconds equals 6 seconds. All right, so we have an idea of how much time will be passing as B is moving. I'll record my position versus time for item B. So I'm at 0. I'll assume at a position of 0. At a time of 1, moving at a velocity of 2.5 meters per second. I'm at a position of 2.5 meters at 2 seconds. 5 meters at 3 seconds. We've moved an additional 2.5 meters. Whoops, that's going to be 7.5 meters. Hold on a moment. So an additional 2.5 meters above 5 meters, 7.5 meters. At 4 seconds, we're at 10 meters. At 5 seconds, we are at 12.5 meters. And at 6 seconds, we're at 15 meters. Hey, so we'll look at our, let's see, B, time and velocity. So at a time of 0, we don't have any information. After 1 second, it's moved 2.5 meters, so 2.5 meters per second. After another second, it's moved an additional 2.5 meters, so 2.5 meters per second. You get the idea. And now the order that we make the motion map and the position versus time and velocity versus time graphs doesn't matter that much. We could do one and then the other, but I'll do the motion map first. Hey, see that I'm going to be going up to a distance of 15 meters, and I have 1, 2, 3, 4, 5 divisions there. So I'm going to go in 3-meter steps along here. It's important that when we make our motion map, especially when we're comparing the motion between two objects, that the scale of the upper and the scale of the lower are the same, so we can actually compare that motion. I'm going to take a look at A. So at a time of 0, it's at a position of 0. This might be a little bit tight up here, but you'll get the idea. At a time of 1, it's at about t equal 1. At a time of 2, it's at 10. T equal 2, and a time of 3, it's at 15. Let me go ahead. I'll put my arrows in there. I know it's moving in the positive direction to the right. Go ahead and put B in there now. All right, at a time of 0, it's at 0. Sorry about that. All right, at a time of 1, it's at 2.5. Something I showed in class is I could draw the arrows as soon as I make my dot or do it afterward. At a time of 2, it's at 5, about there. At a time of 3, 7.5, so halfway there. At a time of 4, at 10, you get the idea. I have to put my times in there. Time equal to 0, I'll fill those out. And so I've cleaned up the motion map up here a bit. Now let's go over to our position versus time graph. We see that our time is going to be from 0 to 3, but over here it's from 0 to 6. So we'll make sure we have enough space to cover that along the independent axis. Our position from 0 to 15. Okay, so I'll have to make sure we cover enough room there. So I'm going to go ahead and label this. Starting at 0, we want to make sure that we get all the way up to 6. Along the vertical axis, I want to get all the way to 15. Looks like I got 1, 2, 3, 4, 5, 6, 7. Although I'm not fond of it, I'll have it in divisions of 3 to expand the graph as much as possible. So starting at 0, 3 meters, and so on. I'll plot the A position and time. So at a time of 0, I'm at 0. At a time of 1, at 5, and I'll finish plotting those. Okay, so I plotted the points, and so I didn't quite have a straight edge, but you can see our best fit line runs like that. And that's our data for A. We'll do similarly with B. So I plotted my points for B, best fit line, something like that. Okay, now to plot velocity, we can get it off of the time and velocity graph, or we could get it from the slope. Remember, the slope of this position versus time is the velocity. We found out over here it was at 5 meters. So, whoops, I've got this laid out. It goes 0, 1, 2, 3, 4, 5, 6 times, same time scale as before. And it looks like we have a 5 meters per second. And here we can see we're moving at a constant velocity. So even though we didn't have a data point at 0, we know that our velocity remains constant at 5 meters per second. And I'll do the same for B. If I look at the slope of this, I find the slope is 2.5 meters per second, which is the same as our calculation for velocity. So at 1, 2, 3, 4, 5, and 6 seconds, it's all about 2.5 meters per second. We didn't have data for 0. We can see that because it's moving at a constant velocity, it did start moving at 2.5 meters per second. So that's our value for B. So there you have it, an example of motion maps, graphing, and proportional reasoning from the T1C1 packet. Good luck.